I want to talk about the Euclidean algorithm, which, as the name implies, was known by Euclid himself. So this is 300 or more years before Christ. Still a very important algorithm in number theory. Before I even say what it does, let's look at a series of computations here. I have integers 4076 and 1024, and I'm going to use the division algorithm repeatedly here. So since 4076 is the larger of the two, I'll take 4076 and divide it by 1024, as shown. And by the way, the computations here are easily done. You've probably figured this out and are already using it, but 4076 divided by 1024 on a calculator, take the floor. This is the floor of 3.98, which of course is 3, and then to get the remainder, 4076 minus 3 times 1024 is the 1004. So now I have the numbers 1024, and this new number 1004 came out. Let's take this and bring it over as the new dividend, and the old remainder and bring it over as the new divisor. So now the division algorithm produces 1024 as 1 times 1004 plus 20. Repeat the process, bring the old divisor over to become the new dividend, the old remainder over to become the new divisor, and one more time. And finally we get a remainder of 0. By this pattern, the next step would be to divide 4 by 0, and that's bad news, and so that's a signal for the algorithm to stop. What does this tell us? Well, let's look at a lemma. You probably already know that in mathematics a lemma is a theorem that's useful but not important enough by itself to be called a theorem. So a lemma is a baby theorem, and let's look at this one, which says that if you're applying the division algorithm, then the GCD of the dividend and divisor is equal to the GCD of the divisor and the remainder. So not a particularly intuitive result in my opinion, but let's prove it and then use it. Proof. Let's let D stand for the GCD of given integers A and B. And now, since R is A minus Q times B, just rewriting the result of the division algorithm, that's one thing we know. Second thing we know is that D divides A. It's a common divisor of A and B. And third thing we know is that D divides Q times B, because we know that D divides B itself already, so it's certainly going to divide any multiple of B. And if we look at this, we know that D divides the first term here and the second term here, so we know D divides R. And of course D divides B by definition, so in fact D is a common divisor of B and R. Notice that we're trying to, this is D here, GCD of AB, we're trying to show that in fact D is the greatest common divisor of B and R. I've now shown that D is at least a common divisor of B and R. So to work on showing that in fact it's the greatest common divisor, let's let another integer C be any common divisor of B and R. And what we really want to show now is that D is greater than or equal to C. So if I have a number that's a common divisor and it's greater than or equal to any other common divisor, then by definition it's the greatest common divisor. So here we go on that. Since A equals QB plus R, we know that. We know that C divides QB because C already divides B, and C divides R because C divides R, it's a common divisor. So we know that C divides A. I know that C divides each term here on the right, and so C divides A. So C is a common divisor of A and B. We already knew C divided B, now we've shown C divided A, so it's a common divisor. But then by definition of GCD, C is less than or equal to D, because D was the greatest common divisor of A and B, and now I have another divisor of A and B, so it has to be less than or equal to the greatest common divisor. But now if I look what I have, D was a common divisor of B and R. Then I chose any other common divisor of B and R and showed that D is greater than or equal to that. So again, by definition of GCD, D has to be the greatest common divisor of B and R, and that proves the lemma. So now let's look at the computations we were doing here in light of the theorem. What this series of computations has shown is the following: that GCD of 4076 and 1024 is equal to the GCD of 1024 and 1004. Again, notice that the lemma says that the GCD of the dividend and divisor is equal to the GCD of the divisor and remainder. So here, the GCD of the dividend and divisor is equal to the GCD of the divisor and the remainder. And so now we just chase this repeatedly down the computation. We apply the lemma on each line of the computation. This is still equal then to the GCD of 1004 and 20. And that's equal to the GCD of 20 and 4. And we know what that is, but I can chase this one more line if I want. That's equal to the GCD of 4 and 0. So any number divides 0, so the greatest common divisor of 4 and 0 is 4 itself. So what is the Euclidean algorithm? It's a way of finding the greatest common divisor. And notice that we already knew how to find a GCD. It was by factoring each of the two integers and pulling out common primes. I didn't factor 4076 or 1024 at all to get the number 4. The Euclidean algorithm works completely differently. I wrote more than I needed to on the previous problem because it was the first one we've done. So find another example. Find the greatest common divisor of 689 and 234. Here's really what you would need to write. 689, applying the division algorithm, divide 689 by 234 on your calculator, take the floor, and so on. This is 2 times 234 plus the remainder 221. Now we take the divisor, 234, divide it by the old remainder, 221. So 1 times 221, and the new remainder is 13. Take the old divisor, 221, take the old remainder, make it be the new divisor. goes 17 times plus 0. Okay, so we got our 0. That's a signal that the Euclidean algorithm can stop. And GCD of 689 and 234 it's 13, or by the lemma, the reason we know that, this is equal to the GCD of 13 and 0, and anytime I have the GCD of an integer and non-zero integer and 0, the GCD is that other integer. So it worked again. This seems pretty slick. How slick is it? It's very slick. There's a result called Lame's theorem that says if I have two integers, and A and B, and A is the larger of the two, then the number of divisions needed to compute the GCD using the Euclidean algorithm is no more than 5 times the number of digits in the base 10 representation of B, the larger integer. So for example, if B has 400 digits in base 10, that's a huge integer, and A is smaller than that, then no more than 2,000 divisions are needed to find the GCD of this 400 digit number and the other one. And 2,000 divisions is horrible by hand, but for a modern computer it's nothing. A computer can do 2,000 divisions in a fraction of a second. So we have these gigantic 400 digit numbers, and the computer can find the GCD before your finger gets off the enter key. On the other hand, the old way of finding the GCD by finding prime factorizations, if I turned a modern computer loose on an arbitrary integer with 400 digits and ask it to find the prime factorization, likely to take millions of years. I mean, just completely undoable. So factoring for a computer is hard, but the related question of finding the greatest common divisor or greatest common factor of a pair of integers is actually very easy. So Euclid knew that he had something good. He didn't even know how good it was, though. In terms of modern computing, this is really important. One more thing the Euclidean algorithm does for us, and that is we can actually work it forward and then work it backward to get us back to something that the GCD theorem we called didn't actually do. We know from the GCD theorem that the greatest common divisor of 4076 and 1024 being 4, the GCD theorem says then that 4 is a linear combination of these two integers. So there's got to be an x and a y out there so that this equality is true. But the GCD theorem never told us how to find x and how to find y. The Euclidean algorithm, working backwards, actually does. So we've already done the computation in the forward direction. Now let's work backward through the steps we've already done in the Euclidean algorithm. So by the forward steps, I mean these here on the first page. And now we're going to run through in the other direction as follows. GCD of 4076 and 1024 is 4. But if I looked at the next to the last line here, here's how to write 4 in terms of 1004 and 20. Let's do that. 4 is 1004 minus 50 times 20. And the line before that, I need to keep scrolling back and forth, the line before that shows us how to write 20 in terms of 1024 and 1004. Let's do that. So I'll recopy the 1004 for the moment, minus 50 times, and a way to write 20 is 1024 minus 1 times 1004. Now if we look at what we have, there's 1004 here, and then there's 1004 buried inside this factor as well. So the next stage, this was a substitution stage here, a substitution stage here. Let's take a simplification stage and group the 1004s together. I have 1 times 1004, and now here's a minus 50 times a minus 1 times 1004. So altogether that makes positive 51 times 1004, and then minus 50 times 1024. Keep in mind what I'm trying to do. I'm trying to write 4 as a linear combination of 4076 and 1024. Here's the 1000, here's 4 equals, and now the 1024 is already in there. I'd like to get a 4076 in there as well. And so if I go back to my first line, here's how to write 1004 in terms of 4076. Let's do another substitution stage. This is 51 times 4076 minus 3 times 1024 minus 50 times 1024. That was a substitution stage. Now let's do a simplification stage. I have several terms, 2 terms, involving factors of 1024. Let's put those together. So the rest of it is 51 times 4076, and now here's a 51 times a negative 3, and then a negative 50. If I work that out, that's minus 203 times 1024. And that does it. I was trying to write, if I can get this on the screen, I'm trying to write 4 as a linear combination of 4076 and 1024. This is x, and this is y. So the Euclidean algorithm has assisted the GCD algorithm, or made the GCD algorithm specific by actually letting us find integers x and y. So that's the end of that computation, and actually the end of the lesson on the Euclidean algorithm. Thanks.